All right, we are going over the first half of the semester exam review packet. So let's get started with gases. List 3 properties of gases. So this goes way back to the first week of school, but just think about what you know about gases. So things like gas particles are constantly moving, right? They're all around us. They're constantly, randomly moving. They don't know where they're going. If you heat up a room, as the temperature goes up, the speed of gas particles also goes up. The average speed of gas particles also goes up. Okay? There are other things too that you could include here. Gases move in straight lines until they hit something and then they ricochet off. They always move in straight lines. And you might have thought of other things too, like gases are compressible. They take the shape of their container. All of those things are great. Draw a picture of 2 barometers. So remember a barometer, the old-fashioned ones, had a dish of liquid mercury with a glass tube, and it was open to the air. So if you had one at sea level, there are lots of gas particles that have force and exert pressure on this liquid, pushing the liquid up into the barometer. Okay, so for example, this height would be 760 millimeters high of that mercury. So they could tell a difference in pressure using this dish of mercury. If they brought it to the top of a mountain, now gas particles are very scarce in comparison. There's hardly any pressure pushing down on this liquid, so it's not going to go up as high. Okay, maybe it'll only go to, for example, 300 millimeters high. That's why it's harder to breathe at the top of a mountain. Higher elevation, it means less gas particles, which means less pressure because they're colliding less. Laura's practicing volleyball. The ball's not bouncing right, so she pumps air into it. So air particles, although they're small, they have mass. So the mass of the ball will go up. If you have an empty balloon and you put it on the scale, and then you blow air into the balloon and you put it on the scale again, that second balloon is going to weigh more. How about converting to Kelvin? You're going to have the formula on your exam, degrees Celsius plus 273 equals Kelvin. So all you have to do is punch in minus 38 plus 273, and that comes out to be 235 Kelvin. Oh, the formula was right there too. What about the opposite? I'll also give you the opposite version. Kelvin minus 273 will get you degrees Celsius. So here we need to do 585 minus 273. That comes out to be 312 degrees Celsius. What's the relationship between temperature and pressure? So it's great to think of examples here. Let's say you've got a box and you've got 5 gas particles in it. If you heat up those particles, they're going to start moving faster, and they're going to collide with the walls rapidly and way more often. That means pressure on that box is going to go up because there are now more collisions exerting force. What is absolute zero in degrees Celsius? Absolute zero, 0 Kelvin, is equal to negative 273 degrees Celsius. Remember, 0 degrees Celsius is freezing to us. So this is really, really cold. And this is when it's so cold that particles stop moving altogether. So obviously this is theoretical. If you were thrown into a room at 0 Kelvin, you would die because your particles would basically almost stop moving. Technically, you'd be heating up the room a little bit, but that would be way too cold for your body to handle. What happens to pressure when volume is doubled? Okay, let's go back to our box situation. Here's 5 particles. Now we're giving them twice as much space. I'm trying to double my volume. Are they going to collide with the walls as often? No, because now they have more space. They're spread out here. So when volume goes up, pressure goes down. That's called an inverse relationship. By the way, if you forget, you can always think about those PTV sticks, kind of like NTV. you put your finger over the thing that you are holding constant. So imagine you're holding pressure constant. If you raise the stick up, if temperature goes up, volume is going to go up. Okay, now imagine you're holding temperature constant. If pressure goes up, this part of the stick, the volume would go down. Okay, and same thing with volume. If temperature goes up, then the pressure must be going up. Draw a picture of why the Coke can was crushed when it was heated and placed upside down in cold water. Well, when you set that can in the really cold water, upside down, so the hole is here, the gas particles that were inside got really, really cold all of a sudden. So they condensed and went back into a liquid. So now there's literally nothing in the can. And what was outside of the can all this time, atmospheric pressure, now it's greater outside the can than inside. So it can crush it. Before, they were holding their own. They were pushing back and the outside pressure was pushing in. It was like a war. But when there's nothing left inside, now outside pressure wins. Number 10. A 5-liter container of nitrogen has a pressure of 4.8 atmospheres. What volume, greater than or less than, would be needed to decrease the pressure? If you want to have these particles collide less often, you need to increase the volume. Now they can spread out and they'll collide less often, lowering that pressure. So the volume needs to be greater in order for pressure to go down. Okay, we've got chlorine gas occupying 75 milliliters at 350 Kelvin. What if you heat up those particles? What's going to happen to that balloon? Well, if you heat them up, those particles are going to start moving faster and they're going to push out against the edges of that balloon with more force. So that balloon, the volume, will increase when temperature goes up. Define mass and volume. Use the terms to define matter. What is an example of something that is not matter? So, mass is the amount of matter in an object. The amount of matter in an object. Volume, on the other hand, is the amount of space an object takes up. Therefore, matter is anything that has both mass and space, and takes up space. What's an example of something that's not matter? So, energy, light, sound. Those are great examples. Things that are, that people forget, air is matter. Air is made of particles. They have mass and they take up space. In the penny experiment, why did it turn silver? It just got coated with zinc. We put it in a dish with a bunch of zinc, and so it wasn't actually silver, it was zinc, which is also silver in color. Then why did it turn gold? Well, zinc plus copper plus heat actually makes brass, which looks like gold, but it was not gold. All right, let's look at these density questions. So you're going to have the density triangle to help you. Density equals mass over volume. This is a divided sign, times sign, divided sign. Those won't be there. So first question, look at what it's asking for first. It's asking for mass. So if you covered up mass with your thumb, what formula is left? Density times volume. It's talking about a piece of zinc. Do we know the density of zinc? Sure we do. Look at this table. 7.1 grams per milliliter times the volume it takes up, 250 milliliters. What is its mass? Multiply and it comes out to be 1,775 grams. Now just think about that for a second. This is saying you've got 250 milliliters worth of zinc. 1 milliliter weighs 7.1 grams. So how much do 250 milliliters weigh? That's why you're multiplying here. Milliliters cancel out and you're left with grams. Number 15. it asks you to find volume. So let's go over to our little formula chart. If you cover up the V, you're going to be left with mass divided by density. The mass, it tells you in the problem, 125 grams. And it's talking about brass. So let's look up the density of brass. It's 8.4 grams per milliliter. Mass divided by volume, or divided by density, is 14.9 milliliters. So let's think about that. You're taking the mass divided by how much that weighs per milliliter to determine how many milliliters you have. All right, 16 is density. Remember, you love it. Mass divided by volume. It looks like a heart. Okay, it's also up here, so you can use that triangle. 34 grams is the mass. 20 milliliters is the volume. 34 divided by 20 is 1.7 grams per milliliter. So which one of these from the above chart does that match? Check it out. It matches magnesium exactly. What are the following measurements? Remember, you always look at what does the instrument go by. Example, this one goes by the ones place. It goes 40, 41, the next line is 42, 43, and it looks like it's exactly on that. So you estimate out one more digit. So this one should be 43.0 milliliters. Graduated cylinders measure in milliliters. Next one, it's between 8 and 9. So again, we're going to measure out one more place. So it looks really close to the 9, so I would estimate 8.9. And we don't know the units. So you can't write 8.99 or 8.90 because the instrument only measures by the ones place, and you can only estimate out one more. Give 2 examples of each of the following. Provide the name and symbol for each. Okay, so nonmetals are things to the right of the zigzag. So look at your periodic table and name anything to the right. Example, oxygen, fluorine. Also an exception is hydrogen. It's to the left, but it's still a nonmetal. Okay? Let's see. Examples of metals. So that's everything to the left. So there's lots of different things you could choose. Sodium, copper, zinc, anything to the left of the zigzag. Now, compare and contrast metals and nonmetals, and what do they have in common? Well, they're both elements. This is a stupid question. Okay? And what are some differences? Metals conduct electricity. They're shiny. Nonmetals are mostly gases at room temperature. They're not shiny. They do not conduct. Explain the differences between an element and a compound. An element is one type of atom. One type of atom. So example, you could have copper and you're talking about one type of atom. A compound, on the other hand, is a chemical bond between more than one type of atom. So example, not just copper, but CuCl2. That's 2 different types. What do the symbols SL, AQ, and G stand for? They stand for solid, liquid, aqueous, and gas. So states of matter. What's the difference between aqueous and liquid? The AQ just means it's dissolved in water. So this one is just salt water. Okay? NaCl liquid means it's molten. It's been heated until it melts. Molten is what I meant to write. It's melted here. Okay, so those are very different. Identify the family that the elements belong to. Bromine is in group 7A. That's the halogens. You need your periodic table that we colored. Neon is in group 8A. All of those are called the noble gases. Okay, so is letter C. Barium is in group 2A. That's the alkaline earth metals. Potassium is in group 1A. That's the alkali metals. Kind of sounds like alkaline earth metals, but it's just alkali. And copper is in group B. That's the transition metals. I'm running out of space. The transition metals, though. What is reactivity? Basically, reactivity is how likely an atom will form a bond. Will an atom bond? The most reactive elements, as far as the metals go, are in the lower left of the periodic table. So that would be things like cesium and francium. Okay, if you're talking about the most reactive nonmetals, that's the upper right, excluding the noble gases. So the halogens, like fluorine. Where are the least reactive? Those are the noble gases. So group 8A, those are the snobby ones that don't like to react with other elements. Name an element that will have a similar reactivity to fluorine. Anything in its same group. So anything in group 7A. So you could say bromine, chlorine. Things with the same number of valence electrons have similar properties. Give the name or symbol for each of the elements below. Nickel is Ni, nitrogen's N, gold is Au, silver is Ag, silicon is Si, mercury is Hg. Then we've got lead, iron, calcium, zinc. So you can't forget your element symbols. Okay? Going back to the models of the atom, billiard ball. They used to think that atoms were small, hard spheres. No charges. How do they think that? Basically, it was just philosophy. Okay, they knew a little bit about chemistry, like energy can't be created or destroyed, but they didn't know a lot, so they just kind of thought about it. The nuclear model, where we've got a hard, small, dense nucleus in the center, a dense nucleus, and they knew that there were protons in there, and electrons orbit. That came from a very important experiment, the gold foil experiment that Rutherford did. Basically, they shot alpha particles at a very thin piece of gold foil, and most of the time, the alpha particles hit a detector on the other side of the foil, so the particles were just going right through. And that's because atoms are mostly made of empty space. But every once in a while, one would ricochet back, which meant there must be something in the center of atoms. That was the nucleus. That's how they discovered it. The electron cloud model is the most modern model. We've got protons and neutrons in the nucleus. And we talk about electrons not in orbit, but in a probability cloud. So it's based on a lot of math. And we cannot know the exact location of an electron. Plum pudding model goes back to the early days. It came after the billiard ball, and they basically had discovered electrons. So they said the raisins are like electrons, and the rest of the pudding part is just positive stuff. They did that using an instrument called a cathode ray tube. They would put samples in, and everything was causing this negative beam of electrons to deflect. So they said, wow, that must mean that every element has electrons in it that are repelling this ray. Finally, the planetary model, okay, that's before the electron cloud model. Okay, they had electrons at fixed distances from the nucleus in shells, which we still know to be accurate or still believe. But basically the reason they figured this out was they would heat up elements and electrons would jump up, and when they fell back down they would only release certain wavelengths of light that were consistent. So that meant that electrons must only be able to jump to specific spots, kind of like how on a ladder you can only step on certain rungs. Okay, so let's go back and talk about the order. The billiard ball was the earliest. Then came plum pudding. Then came the nuclear model. Then came the planetary model. And this is our modern model, the electron cloud model. All right, last page. I kind of already talked about this here, the gold foil experiment, so I'm just going to quickly sketch this again. They had a piece of gold foil in the center, and they were shooting, I'll draw it on this side, alpha particles, and most of the time the particles went straight through the foil and hit this detector. But once in a while they would shoot one and it would hit the small dense nucleus and ricochet back, and they would detect it on this side. So this taught them that atoms are mostly empty space, but they have a small, dense nucleus in the center. Describe our most current model of the atom. It's the electron cloud model. And basically, it's that protons and neutrons make up the nucleus, and electrons make up most of the volume of the atom, and the electrons are described as probability clouds of where they probably are. Probability clouds. And by the way, the nucleus makes up most of the mass. Electrons do have mass, but they're so small that it's negligent. They just don't include it when they're adding up the total mass. Here we go. Which two contribute to the mass? That's what I was just talking about. Protons and neutrons. What about the charge? Protons have a positive charge, and electrons have a negative charge. That's why I always draw them with the little minus sign. So now we should be able to complete a table. If the mass is 40, okay, great. How do we find the number of protons? You have to look on the periodic table at what the atomic number is for your element. Calcium's number 20. That means it has 20 protons. How do you figure out how many neutrons? Well, protons and neutrons make up the mass. So if the mass is 40 and 20 is from protons, that means the neutrons must weigh 20. And because it has a positive 2 charge, that must mean that it's lost 2 electrons, and it only has 18, because normally it would have 20, but the positives are winning by 2. That's why it's a plus 2. So there can only be 18 electrons. Check this out. For the next one, we have 15 protons and 18 electrons. The negatives are winning by 3. So we know whatever this is going to have a minus 3 charge. Let's figure out what element it is. Look up number 15. That's phosphorus. Now, what would the mass be? 15 plus 16 is 31. Okay, how about our last one here? 70 minus 31 will give us the neutrons. That's 39 neutrons. Check this out. 31 positives, 31 negatives. So that means this has no charge. And number 31 is gallium, so Ga. How about figuring out the average atomic mass? Remember these? Move the decimal 2 back on the percentage, so 0.6075, that's how often it occurs, times the actual mass, 38.99, plus the other relative abundance times how often it occurs. Punch that into your calculator, and you should get 39.78, and the units here are AMU, atomic mass units. What's an isotope? It's an atom that has the same number of protons, but a different number of neutrons. So, example, let's write out the symbol for carbon. Carbon's number 6, so we can put a number 6 down here. One of them has 6 neutrons, 6 plus 6 is 12, and the other one has 8 neutrons, 6 plus 8 is 14. So those are 2 isotopes of carbon. Check this one out. Write the isotope symbol for an element that has, we've got to add those together, it weighs 26, it's got 12 protons, that's what helps us identify it. Number 12 is magnesium. How about this one? It's going to make us work. 65 minus 35 is 29. Element number 29, 29 protons, is copper. And the mass is 64, so that goes in the upper left. Last one, explain the difference between core electrons and valence electrons. Valence electrons are the electrons in the outer shell. Nichols number 28. If we write out the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. What's the largest shell? 4 is the biggest number out front. How many are in that fourth shell? 2. So 2 valence electrons. If there's 28 total electrons and 2 are in the outer shell, how many are left in the core? 26. Let's do another example. How about number 20? That means it's got 20 electrons. Let's figure out which one it is. It's calcium. Calcium is in group 2A. That means that it's got 2 valence electrons. It matches the group number. So how many are in the core? 20 total, 2 in the outer shell. That must mean there are 18 in the core. All right, good luck with the second half.